Hello, I'm Bernie Weir, resident LED lighting expert here at ON Semiconductor. Today we're going to be talking about LED drivers for bulb replacement. As the cost of energy continues to rise, significant attention has been placed on regulatory reform to phase out inefficient technologies. Approximately 19% of energy used in buildings is for lighting, and a significant percentage of that is traditional incandescent bulbs, which only convert 5 to 10% of the energy used into light. The remainder is converted to waste heat. So between 2009 and 2016, most large countries will phase out the use of the most inefficient general service lamps in favor of more efficient lighting sources. High brightness white LED technology has improved rapidly and can now compete head-to-head with halogen and CFL lamps in terms of light output for incandescent lighting applications, while offering dramatically improved energy savings and lifetime. In addition, LED efficiency continues to improve while the cost of LED lighting falls at a double-digit rate each year. Since most LEDs are low-voltage devices, they are best driven with a constant current. An LED replacement bulb must include power electronics, commonly called an LED driver, to efficiently transform the power drawn from the AC line into a suitable current and voltage to power the LEDs. A popular LED driver topology is the isolated flyback, which, besides providing safety isolation, also does all the control to regulate the required current for the LED string. Circuitry on the safe low voltage secondary side senses the current and voltage of the LEDs and provides a feedback signal across the isolation boundary to control the power conversion process. The secondary side components include biasing circuitry, a dual op amp, a precision reference, and an optocoupler for feedback, along with current and voltage sensing resistors to monitor the LED current and sense if there is an overvoltage fault. There are some distinct advantages of the classical approach. First, you can easily achieve precise current regulation, and the implementation of this is well understood as it is used by most power supply designers. This approach also makes it easy to implement overvoltage protection in the event that the LED string accidentally becomes open due to a loose wire or a manufacturing defect. Because the LED current is directly sensed, the feedback adjusts for any variation due to temperature, component variation, and the changes in the input voltage, so it can operate reliably across a wide range of operating conditions and manufacturing variations. Conversely, there are some disadvantages. The control circuitry on the secondary side consumes power, so it reduces the efficiency since this power is not converted into light. In addition, the componentry takes up room on the printed circuit board and adds cost. And lastly, if any component fails on the secondary side, the driver must be still designed to fail safely. There's another option that can be considered. It is possible with new control architectures to move the regulation functions required onto the primary side, ideally without any compromises in terms of regulating accurate current and implementing overvoltage protection. While the simplest method to implement primary side control is to regulate constant output power, it has limitations. As the forward voltage of the LEDs change due to temperature and manufacturing variation, the current changes, and normal component manufacturing variations in the transformer, power components, and control IC can change the actual power delivered, even if the LEDs are binned to a very tight forward voltage. Ideally, we'd like to regulate the current and not worry about the changes in LED forward voltage and the normal variation in the transformer and other power components. By removing the secondary side control, we're able to remove 16 to 18 or more components that take up valuable board space. This is especially important if we're trying to implement the solution into an application like an A19 bulb. As you can see, ON Semiconductor has developed an alternative approach that eliminates the need for an optocoupler and secondary side analog and discrete circuitry while maintaining tight regulation accuracy on the primary side. This reduces parts count while simplifying LED selection, saving board space, increasing efficiency, and easily addressing safety compliance. For this example, we're using the NCL30082 from ON Semiconductor, a constant current primary side PWM controller optimized for the challenges in the LED market. By having very tight current regulation, LEDs do not need to be overspecified. This saves cost. Moreover, because the NCL30082 current control accuracy is tightly controlled across a wide forward voltage variation, one design can support multiple bulb designs. For example, for the same 60-watt equivalent LED bulb, More LEDs are required for a warm color than a neutral white. So one driver design can support a range of LEDs, reducing engineering costs and manufacturing costs. As LED efficiency improves, the number of LEDs can be reduced while maintaining the same light output, without having to continually redesign the driver. In this example, we are going to show a compact A19 solution using varying numbers of LEDs with measurements taken at various input voltages to show the current regulation accuracy. We first performed the test while powering only 3 LEDs and increased the number of LEDs to 4 while sweeping the input voltage, illustrating tight current consistency of less than plus or minus 1%, taking into account all the forward voltage variation of the LEDs. We also performed this test using both a good transformer with low leakage inductance and a bad transformer with high leakage inductance. This shows that even with wide transformer manufacturing variation, the current regulation accuracy is very tightly regulated for this solution. We then repeated the test and varied the temperature by 90 degrees from negative 15 Celsius to plus 74 degrees Celsius with no discernible variation in the performance. As we have shown, the NCL 30082 provides a robust, highly accurate primary side control solution for general lighting applications. The A19 bulb application shown in this presentation is only one of the many end applications in which this product can be implemented. Thanks for your time and attention. For more information on the NCL 30082 or other LED lighting products we have at ON Semiconductor, please visit www.onsemi.com.